So in the opening little piece of these notes right here, we've got a bunch of different vocabulary words: zeros, roots, factors, x-intercepts. We've talked about all of them. They're incredibly similar. They're not all perfectly alike, but we have given different definitions. So the zeros of p of x, when we talk about the zeros of a polynomial, what we define that as is any value that makes the polynomial equal to 0. That's why we call them zeros. So any value that you plug in here that would make the polynomial equal to 0. So I'll tell you right now, these are answers that I am just giving you. In case you're watching this and you're like, where did that come from? I'm just giving you these answers. So the zeros, aka the values that make this function equal to 0, there are 4 of them. I'm just going to give them to you right now. They are -3, -2, 1, and 2. And again, if you're wondering where are these values coming from, I am just giving them to you. You're not expected to know where they came from. The roots are solutions of an equation. And so if we take this polynomial right here and we set it equal to 0, the solutions that we would get are these very same answers right here. So the roots and the zeros of a polynomial are actually exactly the same. The only difference between these two definitions are that when you talk about the zeros of a polynomial is just an expression. It's not an equation because it doesn't have an equal sign. But when we talk about the roots of an equation, setting p of x equal to 0 is an equation, not an expression. So zeros come from expressions like this, just the right-hand side, and then roots come from equations. But other than that, they mean exactly the same thing. We get exactly the same answers. The factors of a polynomial are the pieces that you get when you take a polynomial and you factor it down as far as you possibly can. So again, you're not supposed to know where this factorization comes from, but if you were to factor this polynomial down, what you'd get is x plus 3, x plus 2, x minus 1, and x minus 2. And again, these 4 things right here relate to these 4 things right here. If you were to take these 4 factors and set them equal to 0, these are the answers that you'd get. If you set x plus 3 equal to 0, you get -3. If you set x plus 2 equal to 0, you get -2, etc. with these two. So factors are very, very closely connected as well. And then the x-intercepts. Let's take a look at these x-intercepts. So I'm going to put a graphing page on here. And we're going to plot this function, this polynomial that I gave to you. So x to the 4th, make sure whenever you do this you get your arrow out of the exponent, plus 2x cubed, again get that arrow out, minus 7x squared, minus 8x plus 12. Oops, that's 11, 12. Okay, so when we hit enter, we're going to see what all of our x-intercepts are. So here's this quartic function. It's kind of a W sort of shape. It goes down, up, a little bit higher here, down, and then up. And so we can see we've got an x-intercept here. That's at -3. Here at -2. And then over here we have one at 1 and 2. So -3, -2, 1, and 2. And again, we're seeing that just on the graph. Here's the 2 and the 1, and then the -2 and the -3. And again, no coincidence that these values right here are the same as these values. So anytime I talk about zeros, roots, or x-intercepts, those are exactly the same thing. And they come from the factors. All right, so keeping that in mind and knowing that we have different ways to talk about the same thing, let's look at the rest of the section, all about roots and zeros of functions. So we've got this fundamental theorem of algebra. It's a very basic theorem that should totally make sense, but we're going to write it down anyways. So what the fundamental theorem of algebra tells us is that every polynomial equation, let's write that, so every polynomial equation with degree greater than 0 has at least one root. In the complex numbers. So there we go. Okay, so now keep in mind when we talk about complex numbers, we could be talking about real numbers or imaginary numbers. Both of them belong to the set of complex numbers. So basically what this is saying is that all polynomials will have a root somewhere. They might be one or more real roots, there might be no real roots because they're all imaginary, but this theorem basically just says every equation will have a solution, whether it's an imaginary solution or a real solution or a couple of both. All right, so this first example here, we're going to solve these equations. We're going to talk about the number and type of roots. So this first equation right here, with all of them really, we're going to take the left-hand side, we're going to factor it down. We're going to see what we get. So the left-hand side here, the way that we factor this is by taking out a GCF. So we're going to factor out a GCF, and remember whenever you do that, that GCF doesn't just disappear, it just kind of hangs out in front while we factor out and see what's left. So factor out an x here, I'm left with an x squared. Factor out an x here, I'm left with just a 2. Okay, so x itself obviously can't factor down any further, but this is going to be like one little factor right here. And then the x squared plus 2, even though it has an x squared, this is a sum. There's no such thing as the sum of squares. This doesn't factor down any further. So what we do once we factor, remember, is we take each factor and we set it equal to 0. Okay, so even the x, and that is the one that people will forget about because people will take the x and we just kind of put it out front and then you forget about it. But don't forget to set it equal to 0. All right, so we've got x equals 0. That's one of the answers. That's already set and ready to go. So we've got that one. And then this one we need to do a little bit of algebra. So we're going to subtract 2 from both sides. Then we have x squared equals negative 2. And then we square root both sides. Anytime you have a squared, you square root both sides. So x equals, whenever we square root, we have a plus or minus. 2 itself is not a perfect square, so I can't take the square root, but I do have a negative. Anytime I have a negative, I pull that imaginary I out front. And then the square root of 2 just stays exactly where it is. All right, so here's what I have. I have this one real answer. And then right here, remember the plus or minus technically counts as 2 different answers. So I have one real and I have 2 imaginary. So altogether, I have 1, 2, 3 different solutions. And no coincidence, my degree is 3. Keep that in mind. Right here, x to the 4th minus 16 equals 0. So let's start with this left-hand side here. So what I'm going to do, because this is technically the difference of squares, so I'm going to take this left-hand side, I'm going to factor it down. Don't forget about my equals 0. So to get x to the 4th, I have x squared times x squared. And what I need to do is I need to get my negative 16, but I need to make sure I don't have a middle term. So what I do is I take a negative 4 and a positive 4, and that's the difference of squares pattern. So here, these two will multiply to a negative 16, but when I check my outside and inside terms, when I refoil, they'll end up canceling. So I take these pieces and I can set them equal to 0. So I'm going to take x squared minus 4, I'm going to set that equal to 0, and then I can take x squared plus 4, and I can set that equal to 0. So here I'm going to add 4 to both sides. I get x squared equals 4, and then I can take the square root of both sides. So x equals, don't forget when you take the square root, we start with a plus or minus, and the square root of 4 is just 2. So we have positive or negative 2. And then here I do basically the same steps. I just start with subtraction. And then I take the square root of both sides. Since I have a square root, I start with my plus or minus. Since I have an imaginary number under the square, a negative under the square root, I know it's going to be an imaginary answer. The square root of 4 is 2, so this is going to be plus or minus 2i. That's what gives me the negative 4 under the square root. So here I have 1, 2. These are real answers. And then over here I have 1, 2 imaginary answers. Which again means I have 1, 2, 3, 4 total answers, and look at that, the degree is 4. Okay, another one where I factor and then set the factors equal to 0. So anytime that you have 4 or more terms, you're automatically going to be factoring by grouping. You've got no other way to solve this. So we take this bracket that I just underlined right here, the GCF that I can factor out and is an x squared. And then in parentheses, remember, I write my leftovers. So when I take out an x squared, here I'm left with a 3x. And then here I'm just left with a negative 1. Okay, now right here, this second group that I underlined, they both have a 3 in common, so I can factor out a positive 3. And then again, in parentheses, you write down what's left over. So factor out a 3 here, I'm left with a 3x. Factor out a 3 here, I'm left with just a -1. So if I'm doing factoring by grouping correctly, these two should match up, and they do. So we think of the term on the left as one term. Like we think of this as one term, and we think of this as one term. That's what gets confusing to people when we're doing the factoring by grouping. So out of this group right here and this group right here, they have a common 3x minus 1. So we factor out the 3x minus 1, and then we see what we have left in parentheses. So when we factor out the 3x minus 1, all we have left is the x squared plus 3. Okay, so just like I've done with the previous two, I take these two answers and I set them equal to 0. Okay, so here are just a couple quick steps. I'm going to add 1. And then I can divide by 3. So I get 1/3. That's one of my answers. And then this one's very similar to the previous couple problems. Okay, square root both sides. I know that because I have a negative under the square root, it's going to be imaginary answers. I also know because I was taking a square root at all that I must have the plus or minus. 3 is not a perfect square, so all I can do is bring the I out front. Then I have the square root of 3. Okay, so there are my answers. So here's one real answer right here. So I've got one real. And then here are my 2 different imaginary answers. And once again, I've got 1, 2, 3 answers total, which matches up with the degree of my original polynomial. So that's what we're going to write down here in the corollary to the fundamental theorem of algebra. It's kind of like a lesser version of a theorem. So what we write here is this is exactly what we kind of just discovered here. All of the answers that we get all together add up to the degree. So we're going to say a polynomial of degree n So if we use n to represent the degree, maybe it's 4, maybe it's 2, whatever, we say it has exactly n roots. And then a quick little note, that is including repeated roots. And what it means to be a repeated root is something like, sometimes when you factor things down, you get like an x plus 1, x plus 1. It's the exact same factor, so it would be the exact same answer, the exact same root. That still technically counts as 2 different roots. So that's why we say this, including repeated roots. All right, so we're going to use that idea in our next couple of theorems. The fact that if you have a 5th degree polynomial, you should get 5 total roots, whether they're imaginary or real. Okay, so this Descartes Rule of signs, I think it's French or something, it's not pronounced at all like you would think. So we've got this polynomial here. P of x, remember a sub n represents the coefficients, x to the nth represents the variable pieces. Let it be a polynomial function with real coefficients. Then, so now this is going to tell us how many positive real roots there are and how many negative real roots there are. This is going to feel like a very weird theorem until we actually put it into place. Okay, so the number of positive real zeros, meaning positive 4 or positive 10 or positive 1 or whatever, the number that we get is the same as the number of sign changes in the coefficients, or, and here's the weird part, or is less than this by an even number. Okay, so we say it's the same as the number of sign changes. Like, let's look at an example right here. We go from positive to negative, that's 1 sign change. Then we go from negative to positive, that's 2 sign changes. Then we go from positive to negative again, that's 3 sign changes. So that means we either have 3 real positive roots, or it's less than that by an even number. So we either have 3 or we have 2 less than 3, which is 1. And that's true. We, in fact, have 1 positive real root. Okay, so it wouldn't be possible to have 2 real roots, for example. We either have 3 or 1. That's it. Okay, the number of negative real zeros, this one's a little bit weird. This is the same, again, as the number of sign changes. Of the coefficients of p of negative x. And I'll explain that with an exact example. So or is less than this by an even number. So these definitions are going to seem absolutely insane until we look at this next example. So make sure we've got those written down. And then, like I said, let me pull up a specific example on the next page that will hopefully make a little bit more sense. Okay, so let's flip this over. So we've got this example, this polynomial right here. We want to state the number or the possible number of positive real zeros, negative real zeros, and imaginary zeros. Okay, so let's start with the number of sign changes. All right, so it's positive, 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 negative. There's our first one. Okay, so let's write h of x sign changes. So we had 1 sign change right there. Then it's still negative, and then it changes to positive. So there are 2 sign changes. Okay, so we're doing little tally marks here. So we've got 2 sign changes. So they're either 2 positive real zeros remember, or it's less than that by an even number. So, or there could be 2 less, which would be 0. So they're either 0 or 2 positive real zeros. Okay, so now we're going to do h of negative x and figure out exactly what that means from that weird definition on the previous page. So that means we're going to plug negative x into this function right here and simplify. So 2 and then negative x to the 5th plus negative x to the 4th plus 3 times negative x cubed minus 4 times negative x squared minus negative x plus 9. Okay, so let's simplify this up. So negative x to the 5th. If I plug a negative number in here, it is going to come out negative if I multiply it 5 times. Because I'll have a negative times a negative, which is a positive, times a negative, which is negative, times a negative, which is positive, times one more negative, which becomes negative. So if I multiply something that's negative times itself 5 times, it will come out negative. So I'm going to have a negative coefficient there. Here, if I multiply something by itself 4 times, it'll still come out positive. So if I do like a negative times a negative times a negative times a negative, it'll actually come out positive. So this is just the same as x to the 4th. Here, since this is odd, this will come out negative. So this would be a negative 3x cubed. Since this one is even, again, the negative x, if I square it, it's the same as if I just square the x because there's no sign change. Minus negative x, that turns into plus x, and then, of course, plus 9. So let's check the sign changes here. Let's keep a little tally. H of negative x. So this is negative. It changes to positive. That's 1. Changes back to negative. That's 2. Still negative. Changes to positive. That's 3. And still positive. Okay, so there are 3 sign changes. So that means we either have 3 negative real zeros or an even number less. So there might be 2 less. 2 less than 3, of course, is 1. So we're going to think of all of the possibilities that we could have here. All right, so number of positive real zeros, number of negative real zeros, and the number of imaginary zeros. Remember, the total number of zeros has to be 5. We have no choice for that. So all of our possibilities, we could have 2 positives, 3 negatives, and that already adds up to 5, so then I would have 0 imaginary. That's one option. I could have 2 positives. I could have 1 negative. And then 2 plus 1 is 3. I would need to have 2 imaginary to add up to 5. That's another option. Okay, so now I've covered all my options with 2 positive real zeros. Let's say I have 0 positive real zeros. I could have 3 negatives, which would mean I need to have 2 imaginary. I could have 0 positives with 1 negative, which would mean I need to have 4 imaginary answers. And that's it. I think we've got all of our possibilities here. Okay, so we could have 2 plus 3 plus 0, that's 5, 2 plus 1 plus 2, 0 plus 3 plus 2, and 0 plus 1 plus 4. So when we look at the different possibilities between the number of positives and the number of negatives, we then add up and see how many imaginaries that would leave us with. So this is what we're working with here. These are the number of zeros that we could have. Okay, so we're going to do something really, really similar with example number 3. We're going to find all the possibilities and then see what we're working with. Okay, so the number of positive real zeros. I have no sign changes here at all. Okay, so positive, 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 positive. There are no sign changes, which means I have 0 positive real zeros. There is no other choice other than that. So I know that going in. So that's going to make everything a little simpler. To get the number of negatives, let's plug a negative x in here. Okay, so if I plug a negative x into the cubed, it does actually change the sign and come out negative. If I plug something negative in here, it doesn't change the sign, so it's still a positive 2x squared. Here, if I plug something negative in, it does affect it, so then I have a negative 9x, and then just the positive 18. So this is negative. Here's 1 sign change. Here's 2 sign changes. Here's 3. Okay, so the number of negatives. I could have 3, or I could have an even number less, so or 1. All right, so that's what I'm working with so far. So I know I'm not going to have any negatives. I know I'm not going to have any positives, and I know I could have either 3 or 1 negatives. So then my imaginaries will kind of follow suit. So my imaginaries, if I have 3 negatives, then I'm going to have 0 imaginaries. Or if I have 1 negative, then I'm going to have 2 imaginaries. Because remember, your total number of answers has to add up to 3, which is the degree. Okay, so we start with that. We figure out like how many I might have. And then working with our equation the way it is, the easiest thing that we can do is factor down the equation. All right, so we're going to factor down the equation and see where we go from there. So we take this right here. We're going to group these 2 together, group these 2 together. Whoops, sorry, silent phone. So we've got x cubed plus 2x squared. The GCF there is an x squared. And then we put our leftovers in parentheses. So my leftovers here, I'll have an x left over and then a 2. So x plus 2. Then plus, here between these two I can take out a 9. And then in parentheses my leftovers. If I take out a 9 here, I'm left with an x. If I take out a 9 here, I'm left with a positive 2. Okay, so remember just like the previous one when we were factoring by grouping, this is technically one term and this is technically one term. Both of those terms have a common x plus 2. So I can factor out that common x plus 2. When I factor out that common x plus 2, I have an x squared plus 9 left over. Okay, so I take those and I am going to set them equal to 0, because when I'm looking for the zeros, that means I want to know when the equation would equal 0. So I take the x plus 2 and I set it equal to 0. And I take the x squared plus 9 and I set it equal to 0. So here if I just subtract 2 from both sides, I get x equals negative 2. So there is one negative real root. Let's solve here. Okay, x squared is negative 9. Square root both sides. And we get x equals, well, we know the square root of 9 is 3. But the negative makes it a 3i. And every time I square root, you know I have to have that plus or minus. So here's what I ended up with. I ended up with one negative real root and 2 imaginary roots. 1, 2, 3 altogether gives me 3 zeros, just like the degree. Okay, last thing we're going to squeeze in here. The complex conjugates theorem. This has to do with the complex numbers that you're going to come up with when we're solving some of these equations. So what we notice, and let me flip you back through some of these examples. We have the plus or minus 3i. If we look at some of the ones on the previous page, we've got plus or minus I root 3, plus or minus 2i. These are conjugates of each other. You've got 2i and negative 2i. It's not like you had one imaginary number and some other random unconnected imaginary number. You had an imaginary number and its conjugate. That's not a coincidence. That's what's going to happen every single time. So we're going to write a theorem about that. So let a and b be real numbers where b can't be 0. All right, so here's how this works. This says if a plus bi is a zero of a polynomial function, so if a plus bi is a zero of p of x, then a minus bi is a zero of p of x. So this basically says if you come up with one complex number, such as negative 3i, its conjugate will also be an answer like positive 3i, which we've seen from our previous examples. Okay, so our last example here, we're going to write a polynomial function of least degree with integral coefficients having zeros that include negative 1 and 1 plus 2i. So what this complex conjugate theorem tells us is that if we have 1 plus 2i as a conjugate, we have to have 1 minus 2i as an answer as well. Okay, so we've got 1 plus 2i and 1 minus 2i. So we know we've got that to start. Those are some of the answers. And then we're also going to have the negative 1. Okay, so don't forget about this. So when we set up our polynomial function, we know what these factors are going to be. Okay, so we set this up. So x minus 1 plus 2i is going to be one factor. X minus 1 minus 2i is going to be another factor. And then x minus negative 1 is going to be another factor. We're taking these zeros, we're taking this 0, and this 0, and we're plugging it into like the x minus thing so we can do our factors. And then we're going to set these equal to 0. Okay? So what I want us to do is I want to, instead of doing a three-piece, I want us to think of this as one term when we're foiling. Okay, so here's how this is going to work. We're going to have x times x, which gives us x squared. Then we're going to have x times this complex number right here. Okay, so x and then times this complex number, 1 minus 2i. And then we're going to multiply these two together. And since this is a negative, I'm again going to attach a negative, so minus x and then 1 plus 2i. And then finally we're going to multiply these two together. So we're going to have 1 plus 2i times 1 minus 2i. Okay, we're going to mess around with all this. We got lots of things to simplify. So we've got x squared, distribute this negative x, so minus x and then plus 2i times x. Here we have another minus x and then minus 2i times x. And then here we're going to FOIL this out. So 1 times 1, of course, gives us 1. The outside and inside terms will cancel. That's the beauty of the conjugate. And then we multiply these last two. We have a negative 4i squared. And remember, every time I see an I squared, I'm supposed to replace it with a negative 1. So negative 4i squared is actually negative 4 times negative 1, which is positive 4. Okay, so let's clean these all up a little bit. These two cancel. I have one positive version, one negative version. I have an x squared. Combine these up, I have a negative 2x. Combine these up, I have 5. Okay, so that's what I got from multiplying these two together. I'm going to take what I just got, and I'm going to multiply it by x plus 1. Okay, so one more round of foiling. So take x squared times x, I get x cubed. X squared times 1, I get x squared. Now move to the 2x. Negative 2x times x is a negative 2x squared. Negative 2x times 1 is a negative 2x. Then move to the 5. 5 times x is 5x. And 5 times 1, of course, is 5. Don't forget my equal 0 because it needs to be a function. So all I have is this x cubed, nothing to combine it with. Then I can combine these two to get a negative x squared. And then I can combine these two to get a positive 3x. And then I have a positive 5. So I'm going to write p of x for my polynomial equals, and there it is. All right, so we are all set.